To our second day on atomic structure, and today we're going to start with just redefining what we said yesterday. Mass number, remember, is just your protons plus your neutrons. Because of that, you would always expect it to be a whole number. And we said that since it's a whole number, it's not what we see on the periodic table. Instead, what we see on the periodic table is known as the atomic weight, the exact same thing as being the atomic mass. It's probably a little bit more commonly used. And what the atomic mass is a weighted average of all of the isotopes of that element. So all of the mass numbers of that isotope. So let's say weighted average of all mass numbers of all isotopes of that element. Again, this is what we see on the periodic table. And we could also wonder, why is the actual weight, in other words, our atomic weight, atomic mass? No, this is not of the atomic weight or atomic mass. This is just of an individual isotope. Why is it not a whole number? And you'll see this in some examples. I'll bring this up again when we go through some examples. You'll see that it's not a whole number that we use. We don't actually use the mass number. Instead, we use something that's always a little bit less. And the reason is that some of that mass goes into energy to hold that nucleus together. So let's say that some of the mass of the protons and neutrons go into energy to hold nucleus together. So we would expect this to happen because you know that your protons are going to be positively charged, so they're going to repel each other. This all goes back to Einstein's famous formula, E equals mc squared. So we just see that those protons and neutrons, some of it goes into the energy, the mass of those goes into the energy to hold that nucleus together. So when we go through trying to figure out how we calculate our atomic weight or atomic mass, same thing, what we're going to do, it's a weighted average, so the formula that you would use is you would just take the abundance of your substance, and it's a fraction of the abundance, right? It's in fraction form or decimal form, and you take that and multiply it times the mass, and then depending upon how many you have, you just add them all together. So it's a summation of all isotopes. Just that abundance times the mass. So here we have an example of some magnesium metal. And up at the top here it says, write in the atomic number for each magnesium atom. I'm not going to take the time to do that, but based on the isotopic symbols that we did yesterday and looking at a periodic table, we would see that all magnesium atoms have an atomic number of 12, so we could go ahead and write in a 12 in all of these. That's what you would expect. They all have an atomic number of 12. So yes, these are all isotopes of one another. So if we look, it says, what are the mass numbers of the naturally occurring isotopes of magnesium shown in this model? So if I go through and I try and identify all of the different isotopes, I see some 26s, some 24s, and 25s. So that's what we've got. 24, 25, and 26. Well, do all of the atoms of magnesium have the same atomic mass? Explain. And the answer is going to be, and actually this is a little strangely written, they have different mass numbers, and we're going to be able to calculate an atomic mass. So they have different masses to them right now, but we're going to see, based on the percent abundance, we'll be able to get a weighted average for these. So for the sample of 20 atoms, there's 20 atoms that are shown here. We want to draw a table indicating the mass numbers of the 3 isotopes and the number of atoms of each isotope present. So we just said we've got, let's see if I can do this. I'm not sure I have enough room. But if I were to think about mass number, and then also it says the number of atoms of each isotope present. So let's just call that abundance. It's not in percent form, abundance, but it's the number of atoms at least. So we've got 24, 25, and 26. And our abundance is just number of atoms is what I'm going to show here. And if I count this up, I count, let's see, what is it? 16, just trust me on this, because I pre-counted this. I count 16 that are magnesium 24. I count 2 that are magnesium 25, and I count 2 that are magnesium 26. So which isotope of magnesium is the most common in the model? Hopefully you guys can all see that magnesium 24 is our most common. So in other words, if you were just to reach in there, which of course you'd never be able to do, just reach in there and grab one atom, chances are it would be magnesium 24. That's the most common isotope that's in there. And the percent abundance of each of those isotopes, well, if we have, this is a total of 20 atoms, so really all I need to do is multiply this times 5, so that's, our percent abundance would be 80%. This is percent, this is very sloppy, but just go with it here. Here we have 10% for our 25 and 10% for our 26, so that's what we've got. Based on that, if we know our mass, and we know our percent abundance, we can use the formula that we just talked about and determine what our weighted average is, and that's known as the atomic mass or atomic weight. So that takes us to the first example that you have on your paper. And again, this goes back to that question that says, why is the actual weight of an isotope not a whole number? Well, here our masses are not whole numbers. Instead of this being magnesium 24, 25, and 26, instead of having those masses written here, it's slightly less. And again, that's because some of that energy goes into holding that nucleus together. So we're given masses that are slightly less. And our sample, showing 80, 10, and 10, respectively, was pretty close, 80, 10, and 10. So that's the percent abundance of all the naturally occurring magnesium isotopes on the Earth. And so what we want to do now is we want to use this information and just plug it into our formula. And remember, we said it is the summation. I never even really defined what this symbol means. Hopefully you know this from your math class. But it just means the summation. And we're summing it up for all of the isotopes that we happen to have. And we happen to have 3 naturally occurring isotopes in this example. And we are going to take our abundance times our mass. And we're going to decimalize that abundance. We're going to divide it by 100 right up front. So the way we're going to go through doing this, there's a couple different ways we could do it. I'll do it in a table form. But my average atomic mass is going to be equal to my abundance of 0.7899 times my mass of 23.98504. And then I'm going to add that to the next one, which has a percent abundance of 0.1000 times 24.98584. And then again, I'm going to add that to 0.1101 times 25.98259. Now, before you ever even plug anything into your calculator, hopefully you can look at this and say, all right, this is a weighted average. So you would expect it to be a number somewhere between this number and this number. wouldn't make sense if you came up with a number like 60. It would be somewhere between that 23.9 and 25.9. So when you go through this, you get 24.31, which looks reasonable. I also look at my percent abundance and I see I have a whole lot more of my magnesium 24, so I would expect it to be closer to that value than the 26. We're going to use a rule of thumb here, just make this really easy. Let's write this down. Rule of thumb. When going through this, just round your answer, round to hundredths. So round it to 2 past the decimal, and that'll just make it a nice, easy thing. That's just what you see. That's exactly the same thing as what you see on your copy of a periodic table. It's always rounded to the hundredths. So that makes it nice and easy. Okay, hopefully that made sense, except I forgot one last thing that I need to show on here, and that would be my units. And my unit that I'm going to be using is atomic mass units. Remember, those are relative units. Okay, that's our first example. Next one. We go through, notice I did it kind of in a table format here. Maybe I'll do this writing it out more of in a line. But our average atomic mass is equal to, I'm going to take my abundance, that is decimalized, I've divided by 100, multiply it times my mass. I'm going to do the same. I'm going to add it to the next one, 0.279 times 65.9260 plus, I keep going, notice this one would have to be 0.047 times 66.9271 and plus 0.188 times 67.9298. Magically plug that into your calculator, and if you guys need to pause this, I'm going to keep going, but you would plug that in. Make sure you're plugging it in correctly using your parentheses or whatever you need to be using, but double check yourself. Pause this if you need to and give yourself time to see what the right answer is. But you would expect it to be somewhere between this number and this number, maybe weighted a little bit more heavily up here due to those percent abundance that you see. And the answer that I come up with is 65.38 AMU. All right, we've got another one here. Now in this case, it's a little bit different. We're told that the atomic weight of gallium is given to us as 69.72. The masses of 2 naturally occurring isotopes are given to us, and it's gallium-69 and gallium-71. Remember, the masses are slightly less than that. And we want to determine the percent abundance for each isotope. So, a couple things to remember. First of all, I know that the total percent abundance equals 100%. If I were to think about this as in a fraction form, I can think about that as being equal to 1. That's going to help me with my algebra when I go through this. So the first thing I know is my average atomic mass. I know that it's equal to 69.72 AMU. That is given to me right here. So now I can go through and set this up, but I don't know anything about percent abundance. So let's go ahead and plug in an X. And I'm just going to go in order, and I'm going to do it for this one first, since that's what I come to first in my problem. So I take that and multiply my percent abundance of X times 68.9257. And I add that to my other percent abundance times my mass of 70.9249. But now to figure out that other percent abundance, I have to think about the total is 100, but remember when you decimalize that, it becomes 1. So what I want to say here is 1 minus x. 1 minus x. That should ring a bell from algebra. So now you're just doing an algebra problem. 70.9249x, making sure that you can solve for this. And x equals 0.603. So again, stop the video if you need to and make sure you can do this algebra, because everybody needs to go through that. These are the tougher ones. Lots of times you can get it set up like this, but then going through and solving for x can sometimes throw you. Okay, that is not enough. What I've just done is not enough information, but it's a start. So I have just solved for x. I've solved for the percent abundance in decimal form for my gallium-69. So I know that my gallium-69 has a percent abundance equal to, I'm going to multiply this times 100, so equal to 60.3%. Meaning, when I take my 1 minus my 0.603 or my 100 minus 60.3, I get that my other isotope, gallium-71, has a percent abundance of 39.7%. Okay, spend time with that math if you need to. Last one. In this case, I have the atomic weight of chlorine is given to me, and there's only 2 isotopes of chlorine, and they're given as well. So again, we want to calculate our percent composition of each isotope. So I would like you guys to work through this. Stop the video if you are not playing it, doing it in that direction, and then check and make sure you can get the answers. We are going to set this up with our atomic mass equal to our percent abundance times the mass of our first isotope. And then we add it to 1 minus that x times 36.966. So going through, okay, so that means that chlorine 35, this first one, chlorine 35 has a percent abundance of 75.76%, and chlorine 37 has a percent abundance of 24.24%. Okay, last little thing I want to mention is that occasionally you will not be given the actual masses. Remember, we said actual masses are always slightly less. So sometimes you're not given those actual masses. If that's the case, then you should just use the mass numbers that are given in the problem. So for example, this problem tells us that you've got neon 20, neon 21, and neon 22. So you would just set that up. I don't need to go through that necessarily. I'll set it up, but I'm not going to go through. Oops. That should say average atomic mass equals, so we would have it 0.9092 times 20. So I've just done those guys. Plus, make sure you don't let this trick you. You still have to divide by 100. So it's 0.00257 times 21, and then plus our last one of 0.0882 times 22. And you should be able to go through and get an answer. And in theory, those answers that we get should be the same masses that you see on the periodic table. All right, that is really all we've got. Hopefully that was helpful. Talk to you later. Bye.